All right, so we were right here. So let's make sure we go over this at least one problem one more time. So I want the probability of at least one defective. Well, at least one defective is ND, DN, or DD, and that's kind of long to figure out. So what I'm going to do is I'm going to figure out the complement. I'm going to figure out the probability that none are defective and take it away from 1. So all I need is the probability of NN, non-defective, non-defective, which is 96 out of 100 times 95 out of 99. So go back, oops, right here. That's 96 out of 100 times 95 out of 99, and I just make Excel do it. It's right here, I think. There you go. 96 out of 100, 95 out of 99, and you take it away from 1. It's 0.0787. So 0.0788. And there we go. All right, now let's talk about the infamous Monty Hall problem. It's in the movie 21, and it's all over the place. You're on a game show, and you're given the choice of 3 doors. Behind one door is a car. Behind the other door is goats. You pick a door, say number 1, and the host, who knows what's behind the door, opens another door. He says, say number 3, which has a goat. He then says to you, do you want to pick door number 2? Is it to your advantage to switch? Well, without giving too much away, the answer is yes. It is to your advantage to switch. But let's figure out why. And there are a lot of applets online for this particular problem. One of my favorite ones you can get to by typing tinyurl.com/montysim. Yeah, that's fine. All right, so it's saying select one of the 3 boxes. So I select, and it opens up a goat. Ta! And it's giving me an exclamation point. That was my first choice. Do I want to change to the question mark, or do I want to stick with what I've got? And let me change it. I'm going to change it. Oh, I got a goat. Oh, no. All right, then it gives me another. So notice here I changed. I switched 1 time, and I lost. Let's do it again. I choose. They show me a goat. I change. I win. Do it again. I choose. Show me a goat. I change. I win. I'll choose this one. They show me the goat. I change. I win. And so on. And you can keep doing it lots and lots. You can actually also make it run it. So for example, suppose I'm going to change, and I'm going to have it play the game 100 times. So choose randomly and change no matter what. Let me start it. And then it has it done. When I did that, I won 68% of the time, and I lost 33% of the time. All right, then you can do it again. I could run 1,000 times where I change. Takes just a second. There you go. When I played the game 1,000 times, I win 66% of the time, and I lost 34% of the time. Now, this is empirical results. Actually, this is a simulation of empirical results. But how would it work classically? Right? Because most students, when they see this problem, they're like, oh, it won't matter no matter what. But it does matter. Let's see why. When you choose, oopsie, here, hold on. When you choose, there are 3 options. It could be it could be goat, car, goat. Let me do it this way. Car. It could be goat, car, goat, or it could be car, goat, goat. Now, let's just look at the top row for a second here. And what I do for the top row will hold true for the rest, okay? So suppose it is the top row, and you choose the goat right there. Then he's going to show you the other goat, and if you switch, you'll win. Suppose you choose the second goat. He's going to show you the first goat, and then if you switch, you'll win. Suppose you choose the car. Then he's going to show you one of the goats. If you switch, you'll lose. So if you look at the top row, right, you switch and win 2/3 of the time. Right? You switch and lose only 1/3 of the time. It's a conditional probability. Given that you've already made a choice, I choose my first door and it's a goat, then my chances of switching and winning to the car happens 2/3 of the time. I will pick up right here next time.